Hey everybody. So I want to do this quick lecture about comparing samples. You're going to have a follow-up assignment related to this, and it's going to be similar to what you did in your last assignment where you collected some data and made measurements of means and modes and medians, etc. So get ready to measure some more things, and this time you're going to measure 50 to 100 of two different things, but they need to be something that you would likely compare. So, for example, how do the lengths of a red oak leaves in a sunny spot differ from those that are in a shady spot? So with that, we're going to jump right in here. I want to talk for a few minutes about t-tests and ANOVA. So to start with, how do we tell if two samples are different? So really what we're trying to do is we want to compare the average length of turtles of two different ponds as an example. One pond is nutrient poor and the other is not nutrient rich. Could be sort of an ecological question we're interested in. And we spend several days out in the field collecting measurements of lots of turtles from both ponds. We then average their lengths and they appear to be different. Turtles in the nutrient-rich pond average 25 centimeters, while turtles in the nutrient-poor pond average 21 centimeters. But we need to provide a robust statistical test to decide if indeed those turtles are in the two ponds are different in length. So this would be as an example. Maybe we have population 1 with a mean x1 and population 2 with a mean x2. And those could represent our two different turtle populations. Remember, though, that when we're talking about comparing things statistically, we are comparing samples. So the pond A, every turtle that's in that pond might represent a population, and the same for pond B. All of the turtles would represent the population. However, and despite the fact that we spent a lot of time sampling turtles in the pond, we probably didn't capture all of the turtles. And so we want to compare the two ponds, and based on the number of individuals we have, the mean value, and some variance around the mean, we want to be certain that our analysis and our conclusion that we come to is statistically significant or not. So, and you could think about maybe in pond A, it was when we spent a full day there, it was rainy, and so turtles were less active because they are poikilothermic, and therefore they don't spend as much time out and about during those cool, rainy days. Whereas pond B, it was warm and sunny, and the turtles were more active, so we may be more likely to catch more turtles. All right, so we need to talk about a p-value. So the reason we do this is statistically, this is how we make the decision as to whether or not something is in fact significant. So p-value is the probability of obtaining results as extremed as the observed results of a statistical hypothesis test. This value is adjustable, but generally speaking, scientists use a 0.5 as the cutoff. So if you want to be more stringent, so for example, sometimes in clinical trials, you might use a cutoff of 0.01, or if you are willing to take the risk, so maybe there's, for example, with COVID-19, because there might be the need for a drug to combat the COVID-19 is so high, and maybe the cost of doing so is relatively low, then you might be willing to be a little more flexible there, and you may see 0.1. So generally speaking, the smaller the p-value is, the more confident we are that those differences that we observed are in fact different. And you can see in the figure below at the bottom of the slide, those areas out in the tails of the distribution are where this area that we're talking about p-value. So essentially those areas are in this area. If we're talking about 0.05 or 5% of the distribution, this would be this would be 2.5% of the distribution, and this would be 2.5% on this side. So the student t-test allows us to make statistical comparisons between two samples. The student t-test is pretty neat how it got its name. The guy that invented the student t-test worked at the Guinness Brewery and came up with this analysis and this way to compare things like barley and things like that, yield and whatnot. And wanted to publish it, but Guinness wasn't really happy about him publishing it because of the tie with the company. So he decided he would publish it. He finally published it under the pseudonym Student. I've got a video that's in the module that you can watch that tells you a little bit more details about that, as well as more about student t-tests and distributions also. So, is the distribution, the length of turtles in pond A different from pond B? And I'm going to show you in Excel and Program R how to do a student t-test. Okay, so that's all in good. So now we can compare these two different samples, and we'll look at how we do that in a minute. But what happens, oh, and this could be our distribution that we looked at earlier. But what happens if we have more than two samples that we're interested in comparing? We could use multiple student t-tests, but one, it's sort of time consuming to do multiple tests, and two, there are some statistical issues with that as well. I'm not going to get into that, but there are, just be aware. So what are we to do? We use analysis of variance, or ANOVA. And so in this example below, you see that we have pond A, pond B, and pond, that should be pond C. So pond A, pond B, and pond C, we're interested in whether or not the length of the turtles are different in those three ponds. And so you can see here that group 1, 2, and 3 would represent our ponds, and the vertical lines would represent our means. So we want to know, are they different? I'm going to show you how to do analysis of variance in Excel and in Program R also. So let's jump into that. To start with, let's go with Excel. And I'm using this time a data set that is available in the Tidyverse, which is a library or package in R. This is called, I think it's actually called miles per gallon, or MPG. But anyway, it has multiple car manufacturers, their model, their displacement of the engine, the year, the cylinders, the transmission type, the drive, the city miles per gallon, highway miles per gallon, I can't remember what FL is, and then the class. And what I'm really going to try to do here is compare the miles per gallon in the city to the, based on their engine size, so cylinders, 4, 6, or 8. All right, now in Excel, you can see the structure of this data set, and this is how typically we enter data into a spreadsheet. This would be sort of how you would enter data in your grade book, for example, where this would be student 1, 2, 3. This would be observation 1, 2, 3, etc. But in Excel, you have to sort of rearrange the data in order to do t-tests and analysis of variance. So I've already done that. I'm going ahead and done that ahead of time. And you can see that we have 8-cylinder, 4-cylinder, and 6-cylinder. I know that's a little confusing, but that was the order that they were arranged in alphabetically. So anyway, so now I did a t-test that is 8-cylinder versus 4-cylinder. And you can see that the p-value, I can type in, this is the p-value, is much less than 0.05. In other words, we can be pretty confident that that the miles per gallon in the city is different between 8-cylinder and 4-cylinder cars. And you would expect that. I think most of you probably realize that if you have a small 4-cylinder versus a larger 8-cylinder like a truck or something. So then we compared 8, I compared 8 versus 6, and then 4 versus 6. And again, you can see that they're all significantly different. One of the things you'll notice is that as we move from 8 versus 4, 8 versus 6, and 4 versus 6, the closer we get to the smaller the engine, we end up with p-values that are closer to our 0.05. However, they're still really far away from 0.05. Now the code, and I know some of you were a bit confused by my terminology there, so the code that I use is just the formula that we use to calculate this in Excel, and it's more traditionally called code in working in Program R or SAS, if you're familiar with that. And the code or formula that I use is just this. It's t.test. You have to, of course, type equals, and I can do that here just as an example. You say equals t.test, parentheses, then you want to do, so if we're going to compare the 8-cylinder, select that column, comma, 4-cylinder, select that column, comma. You're going to do two tails and paired. And and then you hit enter, and there's the value that you see above. So there, and there. Okay. Now, we can do, as you see, I did this. It takes a little bit of time. It's not a huge thing, but it takes a little bit of time to do 8, 4, and 6. But you can imagine if you had lots and lots and lots of t-tests you want to do, this could become sort of tedious work and cumbersome, etc. So let me go ahead. Actually, let me switch over to program R and show you how to do a t-test in R, and then we switch back to doing ANOVA. So in R, the first thing you always want to do is set your working directory, which I have done already. There's library tidyverse. ggplot is just sort of the plotting software in the background. I pulled in this miles per gallon data set, as I was telling you earlier, from ggplot2, and I labeled it cars. Then I wrote it out to my hard drive and called it cars as a CSV. And then I pulled it back in after I had changed the number 2, 4, and 6 to the word 2, 4, and 6. I'm sorry, 4, 6, and 8 to the words 4, 6, and 8, and pulled it back in. And you have to do that in R because it doesn't recognize numbers for factor type analyses. Then I went ahead and took a look at the structure just to be sure. So str is structure of the data set cars, and you can see below that it has all of our information in it. The years is an integer. Here's the cylinders. So that was, there were 4, 8, and 6, and you can tell now that it is a factor. And then I went ahead and to do a t-test in Excel, and in R. Remember that you need to, you can only do this one comparison to the next. And so I had to do a subset where in program R where I only considered 4-cylinder and 6-cylinder to make the first comparison. So if I can say, okay, and I called that cars dot sub 1, so subset 1. And then I'll hit go for that. And then for the t-test, you have to name the t-test something, or you don't have to, but I named mine t.test1 as the comparison, and I will go again. And you can also click run for those of you that like point and click type things. So if I click back here, you click run, and then you can look at the results by typing t.test, and you can see that the comparison between our two samples is indeed different. Now, let's switch back to Excel to look at how to do an ANOVA. So some of you may have in your Excel, may have this already, but typically there is another tool down at the bottom or the far right over here that shows that you have to open to use to calculate a t-test, or an ANOVA. However, it's not always visible, so I wanted to show you how to do that. So if you click on File and go to Options, and this Excel Options box pops up, and you need to go to Add-ins, click that. Then you want to select in these inactive application add-ins, Analysis Tool Pack. So you click that, then you go down below and say Go, and then you want to click the box, and I always just click Analysis Tool Pack as well as the Tool Pack VBA, say OK. And now you can see data analysis appeared in the upper right. So I select data analysis. There are a lot of tools that sort of pop up. I'm going to go an ANOVA single factor, say OK. The input range, you just select all of the columns that you're interested in comparing. So that's columns A through C. They are in columns, so be sure that columns are selected. And then you want to let it know that the labels are in the first row, so 8, 4, and 6. And then you can have it provide the output in a new worksheet, but you can also have it provided within the worksheet that you're operating in. So you just click Output Range, and then you select this box. Be sure you click in the box, and I'm just going to put the output right here in L, and you just say OK. And to expand that a little bit, and you can see now that we have a comparison, an analysis of variance that shows comparison between our 8, 4, and 6-cylinder cars for city gas mileage. And the p-value. So here's our p-value. So you can tell that it is indeed significant. There are somewhere there's a significant difference between 8 and 4, 8 and 6, or 4 and 6. So how do we know whether or not there is indeed a significant difference or where it is? And you could do a t-test here between those, but again, there's some issues with that. You have to do some correction. So there is an analysis that you can use. It's called Tukey's honest significant difference, and I'm going to show you that in R. So to do an analysis of variance in R, I did AOV 1 because it's AOV, analysis of variance, is the function that you use. And then I did city as a function, so that city gas mileage is a function of cylinders, and used cars as the data. And if I say run, you can also hit Control Enter, as will provide that result as well. And then if we do that again, you can see in our results down here in our console that we have a significant difference, but we don't, again, know where it is yet. So we use Tukey's honest significant difference, and if I hit go, I ran the analysis, and it's the function is just simply Tukey HSD with a capital T, and then I called it Tukey's 1, and then if I take a look at those results, you can see that we have a difference between all three comparisons. 4 and 8 are different, 6 and 8 are different, and 4 and 8 are different. So with that, I hope that helps, and be on the lookout for, or I guess next you'll find the work that I want you to do in terms of comparing two or three, I think just two actually, two different things of your choice that you get to measure. Try to make them somewhat ecological if you can. I know that we're in a weird situation with everybody being at home. I know somebody measured books in their house, I believe the height of books maybe, in their house for their last analysis, which is funny because that's actually what I did when I had a course similar to this in working on my master's. And then there will be, of course, a quiz related to this as well. I probably will stay away from doing, well, I was going to say I may stay away from doing analysis of variance, but I may have you guys do analysis of variance as well using Excel or R, whichever you prefer. So hope everything's going well, and we look forward to seeing you again here soon.